Hey guys, so in this video we're going to be doing an HSC style question and we're going to end up proving this formula for pi on 4 which you may have seen before, and yeah, let's get into it. I'll just hide these. So part 1, we have to show this thing. Now the first thing to note that is this is a geometric progression, and we can see that because there's a common ratio of minus t squared. So you can think of the first term as being like t to the 0, and the series goes like this. So you can see the terms are going up by 2 each time. And since the sign is flipping from minus to plus, that's the same as just multiplying it by -1. That's why the ratio is minus t squared. First term is t to the 0 equals 1. But the number of terms is a bit more difficult because not only are we going up by 2, but we're also ending up on 4n. However, there is a really nice trick we can use to count the number of terms. So what we'll do is we'll take the index of each term and just write them out as just a row of numbers. And even though these series are totally different things, the key insight is that they have the same number of terms. And that's because for each term in this series, we put a term in the new series because you just get them from the indices. So since we have that kind of one-to-one mapping, it means that the number of terms must be the same. And if we were to divide each term in this series by 2, we would still have the same number of terms because there's that one-to-one mapping going on. And now it might be easier to see that there are 2n plus 1 terms. But if that's not easy to see, then consider this as an example. So if we have the series 1, 2, 3, 4, well, this has 4 terms. And notice that the last term correlates with the number of terms because we start from 1 and go up by 1. Similarly, if we had the series 1, 2, 3, 4, blah blah blah, n, we would have n terms. And if we started from 0, well, that's just adding one more term, isn't it? So we would have n plus 1 terms. So that's why this thing has 2n plus 1 terms. So we just need to find s of 2n plus 1, which is equal to a r to the 2n plus 1 minus 1 over r minus 1. That's just the geometric progression formula. A equals 1, so we can ignore that and we'll sub in for r. Multiply both sides by -1. And I'll just distribute the power inside the brackets. So now notice that this thing, the 2n, is an even number, so 2n plus 1 is an odd number, and -1 raised to an odd number like 3 is always -1. So I have a double minus, which will be a plus. That'll be 1 plus t to the 4n plus 2 over 1 plus t squared. And as a reminder, that's equal to 1 minus t squared plus t4, and so on to 4n. Now, this thing, so the denominator is positive, and this thing's also positive, because it's just equal to t to the 2n plus 1 all squared. And that means if we take it away, the series gets smaller. Hence, we'll have 1 over 1 plus t squared will be smaller than 1 minus t squared, and so on. And that's what we wanted to show. Okay, so for part 2, we have to find this series and then show that this series, which was our original series from before, is less than this thing. So this is also a geometric progression. You can see it's very similar to the one before. A is equal to 1, r is equal to minus t squared. And remember, the first term had the first series had 2n plus 1 terms. So this one will have 2n plus 2 terms. So now we just have to find s of 2n plus 2 is equal to a r 2n plus 2 minus 1 over r minus 1. And the same process as before. Notice this time it's even, so the negative goes away. Oops. And that's equal to Alright, so we've found the sum of the series. Now, since this thing, including that minus sign, will be negative, since these are all square, they're positive, that means if we take away that negative, it will get bigger, because we're essentially adding to it. So it'll be greater than our series. And then we can just move this over to the other side, and we will have remember the inequality sign is pointing from this to that, so it'll be going the other way, just of how we wrote it. So we'll have that, which is what we wanted to show. Okay, so part III. So to start this question, I'll start by writing out the inequalities we had shown from the first two parts. And the questions actually told us what to do here by integrating from x to 0. So we can just slap some after new line. Now, and if you're wondering why the integral doesn't change the sign, it's because we're simply adding. I'll show it to you this way with a graph. So let's say that this is that's a graph of t, and that's just y. So maybe this could be like 1 over 1 plus t squared, and this thing could be our series, which is that. And as you can see, the series is greater than this term, and the integral from x to 0 will also be greater than that thing. Right, this area is greater than that area, which is because this function is greater than this function. So that's why the signs don't change when you integrate. So now this becomes an inverse tan. That's a standard integral. This is just power up divided by new power. Now, Note that when we sub 0 into these expressions, they equal 0. So over here we have inverse tan of 0 equals 0. If you sub 0 into all of these things, that's just 0 minus 0 plus 0, and so on, to equal 0. And over here, inverse tan 0 equals 0, and this also equals 0. So when we sub in 0, we can just forget about it. We just subtract 0. So just forget about that. Just ignore. Just focus on the x's. So we have inverse tan of x is less than x minus x cubed on 3, and so on. And that is what we wanted to show. Alright, part 4. So what's happened over here is, you notice that we now have an infinite series. So that's a hint. That's a big hint that we maybe took the limit as n goes to infinity. So we can just try that on this expression and see what happens. So so when we take the limit of the middle section, there's just going to be an infinite number of terms. So it'll just be this series. And then on the right hand side, we'll have this thing. Now, the question has told us a key piece of information, which is that x is between 0 and 1. And if we have a number between 0 and 1, and that even including 1, and we raise it to a really large power, it becomes really small. And if it's 1, then it just remains as 1. And because of that, it means the limit, it means that this thing over here is going to equal 0, because the top is going to be between 0 and 1, and the bottom is going to be really large. It's going to go to infinity, which means that 1 over infinity, it goes to 0. So we're sort of saying that, yeah, like the limit as n goes to infinity doesn't affect the inverse tan x because there's no n. So in a way, since this thing kind of buggers off, our sum, in a way, gets squeezed between the two inverse tans. So as we add more and more x terms, the graph would look, something like this. That's going to be our inverse tan x over here. This would be our inverse tan x plus that other junk. And as n, and the thing in the middle, I'll just draw that in there. And as n becomes larger, this thing's going to get, smaller and closer and closer. And remember, the sum in the middle still has to be between them, so it kind of gets squished. And we can say that inverse tan x is equal to x minus x cubed on 3 plus x5 on 5, and so on for 0, x1, of course, which is what we wanted to show. And now we've just got the last bit, which is pretty simple. So we'll take this series and we'll just sub in x equals 1. And if you remember, tan pi on 4 equals 1, so inverse tan 1 equals pi on 4. So we have pi on 4 is equal to this sum, which is what we wanted to show. There we go. Pretty simple.